Good morning, everyone. My name is Francesco, and I'm a PhD student at Delft in the propulsion and power and aerodynamics group. And my project is focused on the rotating stall inception in a compressor and into prediction of the operating range of the machine. And I'm a recent beginner to SU2, so don't blame me if something doesn't look like it. So this is a high-speed radial compressor, which has been designed at Delft from my colleagues in the past. And the flow field is characterized by different phenomena. And one of the most important performance indicator of these machines is the operating range. This is a typical characteristic map of the compressor, where you have the total pressure ratio depending at the mass flow rate of the machine for different rotational speed of the impeller. And the operating range of the machine is delimited from the choke line at high mass flow rates, where the channel is choked, and at lower mass flow rate from an instability line, which can mean the triggering of different types of instabilities. And it's very difficult to predict numerically this instability line. So industry still rely on very expensive experiments or scaling laws, which depends on the test data of the company. So it's very important to have a tool that can allow the designer to predict this instability line from the early stage of the design. What happens at low mass flow rate? Just some recall from aerodynamics of compressor. When you reduce the mass flow rate, you are increasing the incidence at the leading edge of the blade. And at a certain point, one of the blades will stall, and it will create a local blockage that will affect the incidence of the neighboring blades. The final result of this is that the blockage flow will just start to rotate around the annulus of the machine at a fraction of the rotational speed of the machine. And this is an example from a high-fidelity simulations performed at KTH from Sundström. And this is the rotating stall pattern, where you have zones of high and low pressures that rotate at a certain fraction of the rotational speed and create vibrations and fatigue failure. So this is a situation that you want to avoid during your design. In the literature, there are 3 different classes of numerical prediction models to predict when these instabilities occur. And the first one is a high-fidelity CFD, which in this context refers to full annulus scale-resolving simulations. And this is very expensive because for this kind of simulations, you need a very fine mesh to resolve the boundary layers around all the blades of the machine. You need a lot of time steps to accurately resolve the transient of the machine, and you need to resolve for many rotor revolutions because the instability takes a long time to develop and to trigger. So this is something that you probably don't want to do during the early design process. Then people develop reduced order model for CFD, where basically you try to replace the physical blade's presence by means of source terms. And these source terms in the turbomachinery literature is called the body force models, where basically in the momentum and energy equations, you introduce some source terms that mimic the effect of the blades on the flow. And then there are linearized stability analysis methods, which just use control perturbation theory to understand how the flow field is stable or not to infinitesimal perturbation. This is a very cheap kind of model, and it would be very useful, but usually doesn't work that much well for high-speed compressor case. So today we'll focus on reduced order model for CFD and their implementation on a tool. So basically you have, this is the meridional plane view of an axial compressor stage, where you have a rotor and stator. And if you look at what happens at the blade rows, you basically have that the blades exchange with the flow a force that can be decomposed into components. And the red components just represents the effect of the viscous losses on the flow, so the increase of MVT and the losses. While the green component is the effect of the blade on the turning of the flow. So it represents the increase of angular momentum that the blade gives to the flow during the action. So basically the idea of body force model is to get these body forces, model them in one way or another, depending on what kind of model you want to use, and distribute them all around the annulus of the machines where the blades are present, making the assumptions of an infinite number of blades distributing these body forces all around the annulus of the machine. Basically, you want to use a very simple mesh which doesn't take into account the physical presence of the blades, and you want to include the source terms in the regions where the blades are present. This allows to have a much coarser mesh, much bigger time steps, and allows you to perform time-accurate and steady simulations at a fraction of the cost of the high fidelity. One thing to take into account is the blockage effect of the blade, which you have it here. So due to the thickness of the blade, the real through-flow passage area is reduced by a factor B, which is called blockage factor, which is a value that is lower than 1 where the blade is present, and this becomes 1 out of the blade. So you have a 1 value at the leading and trailing edge, and soon goes to values smaller than 1 that represents the blockage on the flow. And then you just integrate the conservation equations in the same way that you do with the standard CFD, but you have to keep into account the fact that the volumes and the areas where you calculate the flux are reduced by this blockage factor. Now, in the turbomachinery literature, it's common to shift these blue terms to the right of the operator using vectorial identities, which allows you to avoid messing up with the convection schemes that you usually use for these terms, which you can treat with the standard Brans or Euler solver as it's done on SU2. And you can introduce these terms, which represents the force that the blades exchange with the flow and the effect of the blockage terms by means of another solver, which was initiated from Evert some time ago, which is a BFM solver, which is strictly coupled with the math solver. And this is what you need to perform a simulation. So basically, SU2 wants a mesh pi, which is the standard mesh pi that you give to SU2. And then he needs a BFM input file, which tells SU2 where the blade is present, how much the blockage is, and how the local camber of the blade is inclined with respect to the flow. To obtain this information, you start from the typical hub shroud and blade points, which are the starting data that you always have when you want to analyze a compressor case. And we developed an independent Python module that, starting from these coordinates, gives you the SU2 mesh and the BFM input file. And depending on your body force model that you want to use, if it is calibrated or not with CFD runs simulations or not, this is also, of course, embedded with TurboGrid, which is a mesh generator for runs simulation, and the SU2, which performs the run simulations that you use to calibrate the body force model that you then use for the stability predictions. To see visually this, you start from the blade points. You perform, you obtain the grid, the meridional grid, which is in case is obtained by transfinite interpolation. Then you obtain the data of the blade, so the blockage and the different components of the camber. Then you perform an SU2 run simulations on the bladed geometry. You perform a circumferential average that allows you to obtain the quantities that you need to calibrate the body force model. You extract the forces that should act on the flow, and you just embed those information in the BFM input file and in the mesh file. This is an example of the BFM input file, which is just a text file with the different required quantities. So this is just the geometry and blade representation. And then there are optional quantities that can vary depending on what body force model you want to use. And this is an example of the different mesh that you can use. You can use a 2D mesh to perform a quickly characteristic evaluation of the compressor, or you can use a full anomalous mesh to perform instability calculation. This is the first example I'm going to show. This is the NASA low-speed centrifugal compressor test case. This is an example of a mesh that we used for the body force model simulation. This is the leading edge of the impeller, and this is the trailing edge of the impeller. When you run the simulation, basically you can see the vector plot of the body forces. So this tells you how much the blade, if present, would push the flow, in what direction, what intensity. Just to understand if the simulations make sense or not. And then you can, of course, evaluate the quantities. So they don't get fooled from these very good results because this is a very simple test case. And it worked maybe by chance. You don't know that because if we take a look at the efficiency, we can see that the efficiency is clearly not physical, so it's higher than 1. So we did a step back at this point to understand where the source of the problems could be. So we started from a much simpler test case. This is an ACA profile, which has been extruded in the radial direction. The stagger angle of this blade has been set to 0, so there is no turning of the blade to the floor. And the simulation was carried out without the viscosity effect for the bladed simulation. So this allows to compare Euler bladed simulations with body force model simulations where only the blockage terms are present. This allows you to compute the effect of the blockage source terms if they are implemented correctly. So forth. And we carried out this for different flow conditions, from subsonic conditions to choke conditions, to understand how this behavior was changing depending on the flow condition. This is the reference results from the SU2 Euler simulation. And these are just the expected results that you will get from 1D nozzle theory. And we compare one-to-one the results from inlet to outlet for the bladed simulations and for the body force model simulations. And the uncertainty bar here is plus minus 2%. And the results are quite good, but there are some problems close to the leading edge where, for example, the density has an opposite behavior with respect to what it should have. This is the transonic flow condition. And here I also added different numerical settings that I did on the body force model simulation to understand how the results were affected from the numerics of the simulation. And the final result is still the one that there is some offset from between the body force model and the simulation. And this is just the choke condition, which doesn't say anything else different. And then I started to investigate what happens inside the flow solver. And it's clearly visible that at the leading edge of the blade, a certain amount of mass flow rate, in this case 4%, just disappears from the simulation. And this is due to the fact that you are simulating, for example, a continuity equation with blockage source terms, which are composed from blockage and gradients of the blockage. And if these are not implemented correctly, there is some mismatch. So we are not putting left and right the same terms, and some mass flow rate disappears from the analysis. You can visualize this from the results, where you just compute the residual of your final converged results. And here, the colors are saturated to 100, but close to the leading edge is the zone where the bigger errors are, which is exactly the zone where the mass flow rate disappears from the analysis. And this is shown also in this very simple equation explanation, where you just delete the terms that you don't have, and you compare the convection terms, which are treated from the RANS solver, with the blockage terms, which are treated from the body force model solver. So these terms, in reality, should be part of the same terms. So they should be treated consistently, left and right. So the final result of this is that these terms, the blockage term, should be treated consistently with the convection terms, or they are included inside the convection schemes of these terms, or they are treated as volumetric source terms, but consistently with the other. And just to conclude, a new coupled Euler BFM solver is available on SU2, and you can find on this branch, which was started from ever. Again, thanks. And then a Python independent module is available to generate all the data that you need to carry out the simulations. And 3 different body force models are currently implemented. I didn't talk about them because with the problem of the blockage source term, there was no need to go deeper into the modeling. And then the future plans are to implement correctly the source terms inside SU2 to get sure that mass flow doesn't disappear from the simulation. And then we will introduce body force models that are calibrated with the SU2 RANS simulation, for which the workflow is already available. And then we will finally perform unsteady simulations where we can predict the stability limit. And thank you very much. And if you have any questions.
Thank you very much, Francesco, for this nice presentation. So if I understand correctly, I will ask the first question. So in the new feature branch that you're working on, the problem of this disappearing mass will be right.
Yeah.
So that will be like a couple of days before that.
Yeah.
Okay. So we have to have a little bit of patience before.
Yeah.
A question from the audience? David?
Hey, I was wondering, like, because the goal being to simulate a rotating skull, and if you find a good parallel orbital model and model both the voltage effect of the skull and the increase in emissions.
So there are very different models. Some models are also, can also allow you to simulate the reverse flow conditions that you can have when the compressor is already installed. But since our goal is focused on the prediction on the onset of the instability, we don't need to go that deep into the physics of reverse flow. We just want to understand when the flow field is stable or not. So the normal parallel force model that you implemented at the beginning is probably sufficient to do that.
Thank you, Francesco. Very exciting. Do you already have in mind a test case for validation once it's already worked?
Yeah, one example could be the compressor that Matteo shown for the GPPS, so the TU Darmstadt compressor, which has an extensive data sets.
So they provide stability in data.
For my knowledge, they provide unsteady data. And another compressor could be other test case from NASA for radial test cases. There's a high efficiency centrifugal compressor, which is a high speed transonic radial compressor, which can be used for these validation effects. Thank you.
Well, Nitish, can you go back to your slide where you were showing all the calculations involved?
And this?
No, there was where you showed the entire workflow of all the terms, how it is, yeah, indeed, this one. So now, this was, I find a bit strange, and I understood also from AFL that blockage is not part of the cable and QFS, the normal paragraph. Because I understand that you're taking a simplified definition of blockage.
It's a circumferential blockage. Is a blockage calculated with the thickness in the circumferential direction, not with the thickness in the perpendicular direction to the car. But yeah,
But don't you think that will add more, let's say, accuracy to your solver?
Can be one point that we already thought about it, and yeah, it can be. We also have that data available, so if it's needed, we can switch to.
Because either way, if you are taking just a circumferential blockage, you will never have the peak velocities where you have a circumferential blockage than to a blade line.
Yeah.
Or you always a solution in mind.
This can be a point of improvement. For what I saw in the literature, they usually use the circumferential blockage for simplicity. Some people also don't use blockage terms at all, but can be a point.
So it was ideally developed for this flat, prismatic blades.
No, it has been developed and tested also for blades like NASA Stage 35 has been simulated with this kind of models, and they've simulated the stall limit with this kind of model. And then, of course, if you want to increase the accuracy, maybe you start to tune the different models to be more realistic.
All right. Thanks again, Francesco, for today.